Okay, I'm Enrico from Barcelona Supercomputing Center, and I'm speaking on behalf of the SAFEXPLAIN consortium. I will try to provide an overview of the vision of this project, as well as the use cases we're bringing in, and the concept of the role of the trustworthy AI in these use cases. So SAFEXPLAIN stands for Safe and Explainable Critical Embedded System based on AI. So as the name suggests, we are actually focusing on a very specific type of system and application. These are the safety critical embedded systems which are characterized by the fact that misbehavior on this type of system may lead to unacceptable consequences that may range from endangering human life to huge economic losses to ecological disasters. So that's the reason why normally you need to fulfill very stringent constraints on the qualification or the certification of these systems before being able to deploy them. And you may think about systems you may find on cars, trains, planes, or satellites, but also even in some types of medical devices and power plants. So all these systems are increasingly relying on the use of advanced AI functionalities in order to provide very rich functionality to the end users, and also to dealing with a huge competitive advantage in the market. Nowadays, all the innovation is essentially on software more than on hardware on these domains. The problem here is that the usual practice and requirements for the functional safety certification are clashing with the complexity and the black box nature of AI functions and solutions. In fact, all these practices and requirements are normally applied to relatively simple and white box functions. So the overarching goal of SAFEXPLAIN is to try to make the AI system functions amenable to functional safety certification in order to boost their application and adoption in safety critical systems. And to do so, we need to make sure that on one side, the functional safety is kind of requirements are kind of adapted and tailored to the peculiarities of AI, and on the other side, that AI functions are made amenable to functional safety certification. All these on top of the necessary platform support and toolset support. So the case studies we're covering and exploring in SAFEXPLAIN fall into three different domains: railway, automotive, and space. All these three case studies, they come with the deployment of AI functionality in order to provide some kind of decision making or automation, autonomous operation function. So they all come with a different, with their own safety requirements. They also must comply with different regulations that are kind of domain specific. In any case, all of them are a clear example on how AI-based solutions can be deployed in these type of systems. So we have a different operational environment, as you can imagine, and all these operational environment, they bring a different complexity. We go from the railway scenario, where we are actually interested in monitoring the trails in order to intercept obstacles and promptly react in case of obstacle and reach a safe state. Then we have a little bit more complex scenario with the automotive, where we have a wider spectrum of possibility. You know, the complexity of the scenario is much higher than the one we can have on the railway, with pedestrian detection, road signs detection, and so on and so forth, and planning. And we have an even more complex scenario from the operational perspective, when we have 3D navigation in space for satellites trying to automate the docking maneuver to a spacecraft, and which is a more challenging scenario with the 3D navigation, but also with extreme light conditions. And it's interesting to note that the complexity of the operational scenario doesn't always match it with the complexity of the functional safety scenario, which is associated to these case studies, because the functional safety complexity depends on the criticality of the scenario, which is a function of the probability and severity of the consequences in case of misbehavior of the system. So we are focusing now on the automotive case study. So we are dealing in, as you know, advanced driving assistance system and autonomous driving solution are driving the automotive market in the last years. And all these solutions then kind of built on advanced AI systems to handle a really huge spectrum of tasks in the car. The system goal with a specific use case is to avoid collision with all road users that are identified as relevant for the system. So we are characterized with a large field of view, with the dynamic surroundings, localization of different elements in the road, and traffic signs, road markings, and so on. And we need to provide adaptability to different operational domains. What the meaning of trustworthiness in this case study is, of course, the most logic and easy to grasp the meaning of trustworthy is to be able to explain. To be able to explain the process that lead to the decision taken by the AI function, to be able to provide the factors that led to this decision, the rationale behind this, and the sources of the data used for the decision making to support decision making. This information is crucial for regulatory bodies, for the engineers, for the passengers, and all the stakeholders to understand how and why the AI system took that given decision, and to be able to understand what are the limitations of this type of the systems. But as I was mentioning before, trustworthiness here is not just a property of the AI functions, it's kind of a more a system level properties, because we need to make the AI solution comply with the functional safety requirements. So in this case, we are trying to accommodate this more or less complex automotive use case with the AI perception model and the planning model on top of reference platform for the embedded domain. In this case, we are using an NVIDIA AGX Orin platform with some good level of providing a good level of performance for AI functions, with a score of GPUs and clusters, CPU clusters, and also specialized accelerators for deep learning and vision. And we need to provide support for the functional compliance, both at development and operation for the use case, and to be able to run it on top of this hardware, but guaranteeing controllability, observability, and performance. So I would do that by providing a set of technologies and tools. Essentially, as I was saying before, we're trying to bring AI knowledge inside the functional safety world. So we are providing some extension and adaptation to the functional safety management, which is essentially a set of activities that are performed in order to ensure functional safety in the design and development and operation of a system. So we are extending traditional concept of safety management to accommodate AI concerns. And of course, in doing that, we are also following actively the evolution of standards and regulations that are still immature at the moment to deal with AI concerns. And we are exploiting also explainable AI techniques, for the data explanation and model explanation that needs to be, of course, deployed in order to support explainability of the AI function. In order to do all of that, we are also providing what we call a functional safety software architecture, which is a software architecture patterns that can be adapted to different scenarios of usage as operation of the AI components. This is essentially putting together traditional functional safety concepts. Some of them adapt to the AI peculiarities, and some AI-specific components, trying to allocate and accommodate in a consistent way explainable AI techniques. So essentially, this functional safety architecture allows to provide functional safety compliance by design, by construction. So we are providing specific layers for the monitoring and diagnostic of the AI components. Here we are, for example, dealing with anomaly detection, the input and output, or resource usage, and so on. But we are also capturing AI-specific concern with a supervision function, which is essentially making sure that the operation of the AI component falls in between some safety envelope and accommodates all the explainable AI techniques on the input, output, and on the intermediate steps in the model. And we are also adding
yes, Enrico, sorry, I need to ask you to wrap up.
It's almost done. Yes, almost done. We are also adding software level redundancy and diversity in order to make robustness, to increase the robustness and trustworthiness in the AI component. So what is the future for us in related to trustworthy AI? So trustworthy AI is going to continue to be a relevant concern in the short term, given that AI is now taking pervasive role in every aspect of our life. In SAFEXPLAIN, we already acknowledge that we need for a strong interdisciplinary approach we're putting together functional safety expert, AI expert, regulatory expert, stakeholders. But regardless of the domain, we think that the technology itself alone doesn't allow to reach full trustworthiness. And we need a discussion, cooperation among different stakeholders in order to reach these objectives. 3 upcoming events related to Trustworthy AI in the SAFEXPLAIN. One is going to be a workshop in the 14th of June, collocated to the Reliable Software Technologies Conference. Then we have the digital booth in IDEA Digital Exhibition and a webinar on AI functional safety management methodology. Thanks all, and please follow us on LinkedIn and X. Thank you.